So in the last lecture, we looked at the linear regression, and we are talking about you can say the curve fitting and interpolation techniques in the numerical analysis and computation. So we see that what we did in the last lecture was actually was to, you can say, finalize a formula for which we take the square of errors and use that function to minimize our complete error term. So that we did in the linear least square, you can say, regression. So now we are moving towards the polynomial regression. So we are moving towards non-linear you can say functions or the regression values. One method to fit the polynomials of the different orders to the data by means of the polynomial regression. So the linear least square regression can be extended to a set of n data points x1 to xn with the mth degree of polynomial. So you know that what was our polynomial when we were using the linear function was y is equal to a1 of x plus a naught. Alright, so but you can see if we are going towards the mth degree polynomial, these terms will keep on adding to the you can say our polynomial. Alright, so this was only the basic linear term we discussed in the linear least square regressions. So if it has, you can say, maybe the quadratic polynomial, so it will start with this function. So if it has maybe x3, x4, x5 to xm, we can go on adding, you can say, the mth, go on towards the mth degree of the polynomial. And similarly, the error term in the error term in the linear regression was basically here it was only a1 x plus a naught. But you can see that as our polynomial has now been changed to the mth degree polynomial, so this is basically the y value here. Alright, so our error term will also be modified in the similar manner. So what we did in the linear least regression was that in order to find these values a2, a1, a naught, we take the partial you can say the partial differential of the error term, because we want our error to be minimized. So it will be minimized if we can find the partial derivative and equate it to 0. So we can find all of these you can say constants a naught, a1, a2, similarly am, x, am and am minus 1. So all of these quantities can be found by you can say taking the partial differential with respect to that constant and equating it to 0, as we did in the linear least square regression example. So you can refer to that previous video of the linear least square regression and see how we did that. So basically the main idea will remain the same, but we have now, you can say, more than 3 constants. So as the mth number of, you can say, the degrees of the polynomial will increase, our number of constants will also increase, the number of equations will also increase, and we have to do, you can say, more calculations. So you can say the very first one in the polynomial regression will be the quadratic least square regression. So it means that the higher it will include the second degree you can say polynomial. So it is based on the second degree polynomial. So this is the general equation. So these terms are, you can say, basically the linear terms we studied in the linear least square methods. But this is the new, you can say, term which is having a degree of 2, and there is also one addition of you can say the constant, which is a2. So this is, you can say, the general form of the second degree polynomial. So our error term basically is as we studied in the last lecture, is basically yi minus y. So y basically here is this a2x square. So this is, we have replaced the general form into here, and you can say generalize the expression using um, the summation signs. So now you know that the next step was to find all the constants a naught, a1 and a2. For that we need to find partial e over all these constants. For partial e over partial a naught, we will equate it to 0. Alright, similarly partial e over partial a1 will also equate it to 0, and similarly partial e over partial a2 will also equate that equation to 0, and these three equations will give us these three. You can say after equating them to 0 we can get these three equations, this 1, 2 and 3. So we did the same thing in the you can say the linear least square regression method. If you know, if you have studied and seen that video, then you will see that these are basically the same methods, but instead of the two you can say equations, now we are getting the three equations. And the last time we did was to solve them using the Cramer's rule, and we have to do the same thing here. So these are basically the equations, and we need to find the values of a2, a1 and a0. So this I have stated the Cramer's rule for the three equations in the three unknowns. All right, so these, you can see that these are the three systems of equation, and these are also the three systems of equation. So we can equate these, and we can find that x basically here is representing a naught of our this term, and similarly y here is a1, and similarly z here is a2. Or similarly d1 is this value and d2 is this value. So our a naught will be equals to this x value, which is equal to determinant of this dx value and the d value. Alright, so this is, you can see it's already quite complex, but we can solve this equation using these formulas, and we can equate it. So basically this is the x value here will give us a naught, and this one will give us a1, and this one will give us a2. So after we find this, you can say solve this with the you can say calculators. We can put it in the polynomial. What was our polynomial? Our polynomial was y is equal to a2 x square plus a1 x plus a naught. So when we put all the a1, a2 and a3 from this you can say method, then we can get the best fit quadratic polynomial, quadratic least square regression value for all the data set. So in this example we have to do the same. So you can say that using the quadratic least square regression, find this, f is missing here, find the first degree polynomial that best fits the data in the table. So basically we have 1, 2, 3, 4 and 5 data sets. Alright, so what we need to do is we need to find these summations first. Alright, so we need to find the summations of x values. Alright, so summation of all the x values, similarly summation of all the y values, similarly summation of all the x square values. Alright, so we have other x square, x cube and x4. So we have to find summation of x squares and summation of x cube, and we will put all of these values in these equations. Then we will get it in the form of these you can say system of equations. So we can then apply the Cramer's rule and use these formulas to calculate the values of a1, a2 and a0, and I have just calculated the values a1, a2 and a0. So you can just put and follow the same procedure and then put it in the basic form of our general form of on the quadratic least square method, which is this equation, and we will put the values of a2, a1 and a0 to find this you can say quadratic function. And if we plot this function with respect to the points, you can see that this is not a linear function, this is a quadratic function, and it is best fitting the corresponding points. So you should solve this example by yourself. So I have not included all the, you can say, the process here, but just mention the answers here for your reference. So it is just, you can say, the numerical calculation. You have to use these equations and use these formulas to calculate the values of a0, a1 and a2, and then put it in the general quadratic form to get the function. So now we will move on towards one other method, which is called Lagrange polynomials or Lagrange interpolating polynomials. So this is also, you can say, a polynomial regression. So it could be linear and it could be you can say quadratic and it could be cubic. So the degree of the Lagrange interpolating polynomial you can say can be changed. So the first degree Lagrange interpolating polynomial that goes through the 2 points. If it goes through the 2 points, so you can see that if it is the first degree, it is p1, and we will have 2 Lagrange polynomials based on the 2 points. So the first degree Lagrange interpolating polynomial will pass through the 2 points. So similarly, we will have 2 Lagrange you can say coefficient functions and the 2 y values. So these Lagrange coefficients are given as you can see the relation here. If it is the L1, and then you can say the corresponding other point is in consideration. So it is basically x minus x2, whereas this one value is relating in the denominator, so x1 minus x2. Similarly, for L2 we are using x minus x1, and then this is corresponding to x2 minus x1. So you can use these you can say specific you can say orientation or specific, you can say, arrangement of these formulas to remember them, how to use them. And you see that if the polynomial has to pass between these 2 points, then if we put x1 here in this polynomial, so if we put x1 in the polynomial, it should give the value of y1. So p of x1 must be equal to y1 if it is passing through that point. Similarly, if we put in the polynomial the value of x2, what it should give is the value of the y2. So that will mean that it is passing through that point. So that will happen. So similarly, also this one was the first degree polynomial Lagrange interpolating polynomial. So the basic thing we have to note here is that if it is a first degree polynomial, it will pass through the 2 points, alright, and it will have 2 Lagrange you can say the coefficients. Similarly, for the second degree Lagrange interpolating polynomial, it will pass through the 3 points instead of 2 points, and similarly it will have 3 Lagrange coefficients, and it is basically the second degree Lagrange polynomial. Similarly, we will have you can say the third degree Lagrange interpolating polynomial. It will include you can say L4 also, L4 of, and similarly this will be 3. So these Lagrange, you can say, coefficients here, L1, L2 and L3 are formulated as, you can see that if it is L1, the one term is missing, alright? So we will, you can say, subtract x minus x2 and x minus x3. So 1 is missing from the numerator, and similarly the 1 is representing in the numerator and subtracted from all the quantities. So x1 minus x2 and x1 minus x3. So similarly you can use these, you can say, orientations of these formulas to remember them if you want to. Similarly, if it is L2, you can see that it is missing here. So x minus x1 and x minus x2, and we have to, you can say, use it in the denominator, x2 minus x1 and x2 minus x3. So you can use these arrangements and remember these formulas for your reference. And when we will, you can say, discuss it in the example, then it will be very helpful and you will understand how the Lagrange interpolating polynomials are functioning. So similarly, if the Lagrange polynomial function has to pass, is basically passing through these points, so it will basically satisfy these points. So if we put the value x1 in that polynomial, it will give us the value of y1. Alright, so it means that it will pass through that point. Similarly, if we put x2 in the polynomial, it will give us the y2 value, and similarly if we put x3, it will give us y3. So as we discussed earlier also, the nth degree Lagrange interpolating polynomial that goes to the n plus 1 points, x1, y1 and n points, is equal to, you can say, if it is nth degree, then there will be n plus 1, you can say, Lagrange coefficients. Alright, so you have seen that in the second degree interpolating polynomial, in the first degree Lagrange interpolating polynomial, there was 2 Lagrange coefficients. So the Lagrange coefficient are, you can say, 1 increased in the degree of the interpolating polynomial. And similarly, we can generalize our Lagrange formula with this expression. So basically, if we have n is equal to 2, this means that it is, you can say, the second degree Lagrange polynomial. Then you know that we will have 3 values of Lagrange polynomial. Alright, so this will, the first one will be calculated using this method, and this means that these are the products. So if we put L1 instead of I, you can see that J has to start from 1 to n plus 1. J has to start from 1 to n is 2, so it will start from 1 to 3. So it will give us x minus, so it will start from, you can say, it is not equal to 1 because j and I could not be equal. Okay? So x minus x2 multiply by, because this is the sign here as represented, or you can say as visualized as pi. So x minus, so in the next term it will be 3, so x minus x3, and similarly at the bottom you can see that it is x1 because I is 1 minus, this I and j could not be equal, so j will start from the 2 and reach to the 3, so x minus x3, x minus x2, sorry, and x1 minus x3. Alright, so this is similar to what we saw this formula. Alright, so we can use this this notation also to remember how to use or how to derive these Lagrange coefficients also. So we can now look at one example. So this is the function y is equal to 1 plus e raised to power minus x, and when we put the x values here, we can get these values. Alright, so what we want is we need to find the value of x find the value of this function at x is equal to 0.35, but using only these values. Alright, so we are not calculating it directly by putting the x value here. We know that and our function value at 0.1 is this value, and at 0.5 is this value, and at 0.8 is this. So we need to find the value of 0.35 using this data, not by putting it here. So the first thing we need to do is use the first two data points. Alright, so we will use just first two, 0.1 and 0.5. So it basically these are two data points, so it is basically the first degree Lagrange polynomial. Alright, so it is first degree Lagrange polynomial. And then we will use the second degree Lagrange polynomial that will pass through the 3 points, and we will see that what is the difference between the two in terms of relative error. So the two Lagrange coefficient functions are these. So you can also calculate it using this method, or you can just remember it. So these are the Lagrange coefficients for the first degree polynomial. So because the first question is asking us to use only the two data points and the first degree Lagrange interpolating polynomial, so we will just calculate L1 and L2 and use these formulas which are representing the first degree polynomial. And you know that our first degree polynomial is basically this, and after calculating the value of x L1 and L2, we put these values in our this equation of the polynomial, and we will get this equation. So this is basically, you can say, the function. The y is equal to this function. So if we put now x is equal to 0.35 here, we will get the value of you can say our polynomial at 0.35, and it comes out to be 1.7184. And similarly, if we go towards the next point, which was use the 3 Lagrange coefficient function, which is these are the Lagrange coefficients, and you can remember them, or you can derive them using the general form we discussed, and put the values here. So all these points x2, x3, x1 are given to us, and we can find these Lagrange polynomials and then put in the second degree polynomial equation. So this is the second degree polynomial equation, and when we put these values, we will get this expression. So this is basically the equation, the quadratic equation passing through these 3 points. So now we will put 0.35 in place of x here, and we get the value equals to 1.7065. Now we need to calculate the relative error. So to find the relative error, we must know the actual value. So we can know the actual value by putting 0.35 in the function to get the exact value. So the exact value is 1.7047. So we can find the percentage errors of both the values by putting their values in this function, and we can see that if we were using the you can say first degree Lagrange polynomial, there is 0.8% error, whereas when we use the second degree Lagrange polynomial and use all the 3 data sets that were given to us, we will get only 0.1% error. There are also some drawbacks of the Lagrange interpolating polynomials. It can be observed that none of the information gathered in the construction of the P1 was saved and used in the construction of the P2. So you have seen that for the Lagrange first degree Lagrange polynomial, that is P1x, the formulas for both the L1 and L2 are different than what we have the formulas for the second degree Lagrange polynomial. So second degree Lagrange polynomial has 3, you can say, the Lagrange coefficients, and these values are not interrelated. So we have to calculate the Lagrange coefficient from the very start. So we cannot use the previous iteration again and again. So this is particularly inconvenient in 2 situations. when the exact degree of the interpolating polynomial is not known in advance. For instance, it might be better to use a portion of the set data. So for example, you were initially given 2 points and you use the Lagrange interpolating polynomial to find the best fitting, or you can say the polynomial that passes through these 2 points. So when another point is given to you, then you will have to calculate all of this again using the second degree polynomial. But you cannot use, or you can say not, you can say um, increment your data from this point onwards. All right, so basically you have to do everything from the start. So when the additional points are needed to data to attach, so this is very much inconvenient, because if we have to add on data, so we have to do all the calculation from the very start. So this is, you can say, the major drawback of using the Lagrange interpolating polynomials. So in these cases, a more suitable form is provided by the Newton interpolating polynomial. So Newton interpolating method basically uses this, you can say, our previous calculations. So every point we add to, you can say, every complexity we increase will be, you can say, calculated on top of the other calculation. So we don't have to, you can say, work from the very scratch as we have to do in the Lagrange interpolating polynomials.